This is the 5th video of the series on the suggestions for the theory of everything, and I'd like to talk about how, continuing to follow the theme of how can you get a universe out of nothing. Remember that I said that in the first video that the basic structure of bodies in the universe is nodes of no size or shape separated by lines of no thickness, but nonetheless they do have length, and this framework, this structure, this network is controlled by laws of natural laws that regulate the length of those lines. And the last video I talked a little more detail about that, and I said that the total separation between two bodies represents the total of the energy. It's, the energy can be calculated as the length squared, because energy is proportional to the square of fundamental variables, and that this can consist of a sum of what represents kinetic energy, which is another set of dimensions, and potential energy, which is another set of dimensions. And that a body that is moving has both kinetic and potential energy. A body that is motionless has no kinetic energy. So a body that is motionless, and we're going to talk about motionless bodies to start with, has a total separation that is both its energy and its potential energy. And that, when bodies are not in contact, is a constant. It cannot change. There's no such thing as force at a distance in this model. Now, if you take then a network which consists of units of matter separated by space, you get a body. And I'm going to pick up this body here, which is a spoon, and that's a body of mass. Now, right now, of course, as long as I'm holding it, it's not a separate body of mass, it's part of my body, which is part of the Earth, actually. But if it still has a certain amount of energy, which is total, and if I don't move it, that's all the energy that it has. Now, if I try to bend that, I find that I can't. Now, why is that? Well, it's because the units of matter in here, we won't go into what the structure of matter in the fundamental particles and protons, neutrons, and electrons, and then various elements, and then various molecules of compounds, and then this actually is all those things, plus some of the compounds here are mixed, or it's an alloy of some kind, which means that there are metals in here that are not even chemically combined, they're just mixed. But the forces of the constant energy are so strong that if I try to bend it, I'm trying to stretch some of those separations. As you know, if you bend this, it will eventually break. So I must be stretching it. If I were strong enough and wanted to, it's not mine, so I can't do that. If I try to bend it, I am opposing the energy that's in it, and I have to supply energy. And our bodies are such that if we try to supply energy, it has to come from somewhere, and it comes from my body, it comes from my muscles. And in order to bend this, I have to stretch some of my, shrink some of my muscles. Muscles don't push, they pull. So when I try to bend that like that, I'm trying to pull it in this direction. And muscles in my back are trying to pull it. My muscles in my wrist, controlled by here, but controlling my wrist, all are trying to give energy to the spoon. And I can't give enough energy. I feel the energy going from my body, and I call that a force. And the And what's opposing that force is the strength of this metal, the tensile strength is stopping it from stretching. And this is all because of the laws that regulate the separation between units of matter. Now that's just a little bit of revision really, and I want to now talk, that's why bodies of matter are hard and have some strength. But I should point out that this is not a solid. We call it a solid, to us it's a solid, but in fact it is almost entirely empty space because it is nowhere near as dense as it could be. The density of that would be, I don't know, the iron is about 8 times the density of water. The earth is about 5 or 6 times I think it's 5 or 6 times the density. Now I have to stop and think. I think it's between 5 or 6 times the density of water. Concrete is about 2.5 times the density of water. And the heaviest or the most dense material that we have are metals like lead, thorium, uranium, neptunium, plutonium, americium, fermium, and so on. These are only 18, 20 times, uranium is about 18 times the density of water, which is not very dense. And I'm going to give you an idea of what density would be like if you had an ultimate amount. So I'm going to take a rectangular shape such as this box of chocolates. It's a box of chocolates that weighs about ½ pound. It's almost entirely empty space. And I'm going to just give you a picture of what it would be like if this were fully dense. If this were made up of a rectangular network, a matrix that was like that, and let's just, for the sake of simplicity, instead of having the units of matter moving around since it's not freezing cold or not even coming down to 0 Kelvin degrees, everything is just moving. But assuming nothing's moving, and assuming that the units of matter were in a rectangular network, so that there were lines of force going this way and this way. So you've got a rectangular matrix and in 3 dimensions, like that, so that it was a solid in the sense that it's as dense as it could be. But remember the second law governing the dimensions of energy says that space must be at least one quantum, that's one of the very smallest units. So that this would consist, if it were as dense as you could make it, and still in a rectangular pattern, which is simple, then you would have units of matter, many of them, separated by a single unit of empty space. So it's still almost all empty space, and the rest is nothing. I described that in the first video. So it's more or less nothing, but it is as dense as you can possibly make it. Now that would have be something like the spoon. It would feel solid, but it would be more than just solid, because this, as I said, is only about 8 times more dense than water. This is going to be much more dense. This is as dense as matter can possibly be. There's a name for that. It's called a black hole. How much mass would that have? Well, this would be, if that were as solid as, theoretically, as mass can be, as solid as a body can be, but still have empty space between each of the units of matter, this would be about 100 times as massive as the planet Earth. So that you could get an idea of how I could say that this is almost entirely empty space. It is, because it's by a long, long, long way nowhere near as dense as matter could be. And it is believed that there are, well, it's more than believed, I'm going to say known, that there are black holes, which are probably not much bigger than that, although they are so many, many times more massive than a planet, more massive than the sun. And so now I want to explain what mass is the effect of the forces, and the definition of mass, taking the Einstein's equation E equals mc squared, then mass is equal to energy divided by the square of velocity in dimensions, which is equal to the energy divided by the square of the change of length by change of time. So that mass is made up of energy and length and time, and the energy that we try to change is what gives things the perception of mass. Mass is the perception, and so is force. They are very real to us in human terms of what is real, but in terms of physics, force and mass are just simply functions of the fundamental dimensions of energy, length, time, and matter. So that, I think, is going to be enough. I can't think of anything else I need to cover right now. Force, of course, is the rate of change of energy with distance. And so that's why it is that bodies that have no real solid substance in them can be seen as appearing to be solid and as appearing to have strength, or having strength, and have mass. And if we tried to lift this, we couldn't. And of course, its massive weight of several times the mass of the Earth would cause it to suddenly fall through this table, to fall through this floor. But in fact, being more massive than the Earth, it would not even move. It would stay as it is, and the Earth would come up to meet it, so to speak. And it would swallow me, of course, because the force of gravity, I'm so close to it, that the force of gravity, which is increases as you get nearer to a mass, the way in which it increases is debatable, but it certainly increases as you get nearer. So being so near to such a massive object as this black hole, I would be sucked into it. The Earth would be gradually, it would take maybe some time, because parts of the Earth are a long way away. It's 8,000 miles away on the side of the Earth. So it might take minutes or hours, but eventually this would just get a little larger, and it would be on its own going toward the sun, because of the gravity of the sun relative to the enormous mass here. This, of course, is still going to be light compared with the sun. So the sun will stay where it is, and this will go towards it, and us with it, but we won't know anything about it. So that then is the end of the fifth video, and the next time we'll talk about something else. Thank you for watching this.